Thank you, organizers. Thank you, Kostya, for inviting me to give a talk about that. So here's what I'm going to say. A new result on a long-term behavior of a dynamical system, perturbed by small noise, and which is started near unstable fixed point. And we'll do application or illustration to the bare bones evolution model for an establishment of a mutant. So clearly you can see in this title the effect of long lockdown on a person. You know, it can't be disputed. After 15 weeks of lockdown, you come up with titles like this. I think you need some help. Okay, nevertheless, let's see. So what is first I want to acknowledge people who work on a project, and Jeremy Baker, who is our PhD student, Andrew Barber, who you all know well, Pavel Chigansky, Kais, Peter Jagers, and Hai Kaspi. We started to work with him on this project maybe in 2002, nearly a long time ago. No, 2008, I think, 2008. Yeah. And we still haven't finished the project, it's still going. So I want to tell you about this new mathematical result and some with application. Okay, so let's look at the dynamical system with a small noise, perturbed by small noise. So I'm looking at discrete time, n. So you start at some point x0, and then you have a map f, which maps Rd into Rd, and you generate your dynamical system xn by this rule. It's a dynamical system. So you can also say this is just nth iterate, n plus first iterate. X0, so the subscript will denote the iterate of the function f. Now, what is a perturbed system? That's a stochastic process when at each step you add a noise. So this is noise, let's say call it e to n plus 1, and we put small parameter epsilon in front of it to say the noise is small. And apparently when you look at many physical systems, it makes sense to look at the small noise. Because maybe sometimes coefficients in f are not known precisely, so they have some perturbation with respect to some small random disturbances. In any case, this is a mathematical model, and lots of literature on that. And saying it's a noise, we probably will assume something like that they're centered random variables. Okay, so what is the classical result? So I told you I'm going to say new result. So you have to tell me what the old result is. So the classical result is I'm referring to is a fluid approximation, also known as a law of large numbers. And here we'd like to mention names of Kurtz, Andrew Barber, that's Friedrich Wenzel, people who did work in continuous time setting. And maybe Yuri Kiefer, who did a similar thing in discrete time. Although this result maybe is very simple result, nevertheless, it's very useful as a first step analysis of a stochastic system. So let's assume that f is Lipschitz function with a Lipschitz constant L, and assume that the initial condition of the stochastic system converges to some point x0 as epsilon goes to 0. Then this classical result states that the trajectory of a stochastic system on any bounded time interval, so time interval say up to time n, converges as epsilon goes to 0 to the trajectory of deterministic dynamics. So we'll write it like that. So this is a fluid approximation. So let's say I will thought maybe give a very simple proof of this fact, because it will be a little bit, will show us certain ideas that fail perhaps when we deal with a new situation. So here we use, look at the n plus first step, we write what it is, and here we go using Lipschitz condition on f and triangle inequality, we obtain this inequality. And then, of course, if you can see from this inequality, if you look at this like this, so you can iterate it, you divide by ln plus 1, and you can iterate the system. It's a bit like Gronwall, in discrete time Gronwall, except it's a little bit easier because you can solve the recursion exactly. And when you do that, you can see that you get this inequality like this, because you flip L into the n to the right hand side. Now you can see here that right hand side has no little n in it, so you can put maximum in front, and this inequality holds. And so what we can see from this proof that the convergence holds, provided these things go to 0. So you get two terms, they both have to go to 0, then stochastic trajectory will go to deterministic trajectory. So here we have epsilon comes in two places. The first place is noise. In the second place is initial, the distance. Let's say we'll make it epsilon as well. So the distance of the initial point. So that's an important observation. Anyhow, so you can see from this proof that you don't even have to take constant n, as long as n can depend on epsilon, but these two conditions hold, we have a fluid approximation. Okay, but you'll see when n is quite large, depending on epsilon, then these conditions may fail. And then you don't get, the proof does not give you convergence. So now I want to tell you about the situation which seemingly not captured by this result. So let's look at the situation when point x0 is a fixed point of f. So f of x0 is equal to x0. So it's a fixed point. And what we have in mind is unstable fixed point. Unstable fixed point states that if you start in the neighborhood of x0, the map will take you away from x0, not towards, will take you away. So, of course, if you start at fixed point, that all the iterates is exactly that point. So xn is exactly x0. So if we use our fluid approximation in this setting, we obtain this result, that the maximum, the trajectory of the stochastic system is converges to x0. But as I mentioned, unstable point is such that if xn epsilon, x0 epsilon is not equals to x0, okay? And you act on it with random, with dynamics, even with small noise, it will take you away from x0. So you would have a positive probability to be quite far away after some number of iterations. So this result, of course, is true, but what it says that it doesn't capture this effect. So to capture this effect, to go away from unstable fixed point, you have to take n as a function of epsilon, and also proportional, typically with proportional to log 1 over epsilon. Okay, so will be, if we plug it in there, we'll see that one of these things will be constant, like say 1. And then this result doesn't say anything. So let me tell you now a new result. How can we can kind of correct this result? What is new? So if we take a function, let's at first I wrote it for RD, but I thought let me concentrate on R2 because this working example will be in R2. And let's say we have x0 is a saddle point, a fixed point, an unstable fixed point, and we have number of assumptions. So Jacobian matrix A at x0 is one unstable, so the largest eigenvalue rho is bigger than 1. And we assume this limit. So this is actually the main contribution of our research is this, I think, is this limit. Because various ideas appeared in the literature in some way or another, but this thing I've never seen anywhere. And I talk to people and they haven't seen it. So we look at the limit as n goes to infinity of the n theta of f, but when we start, when you take x0 and we take point x multiplied by rho minus n. So it's a little bit, if we look at fn and act in a linear map. So if you linearize f at x0, you get a linear map. So A gives you the linear, the matrix. So if you get, so the iterates of the linear map is a into the n. So fn takes you away, but you take a minus n back to x0. So we want this limit to exist. And in fact, if we assume it exists, it's not very hard to show the following result, which I'm not going to show this result. I'm going to show a situation where we can prove that this limit exists. So let's now take the norm, let's say infinity of the maximum of x0 to be epsilon as well, and we look at the time log 1 over epsilon times 1 over log rho. Then what we claim that the maximum, so we start the process from t epsilon. And then this process xt epsilon plus n will converge to nth iterate of the deterministic system, but now started at a random point. And this random point is h of w. This very h and w is a random vector of this form, because we have R2, we have only two counts. One will be 0, another will be w, and w is some random variable that we also know how to describe it. And so this is the essence of the new result. So if you start at this near unstable fixed point, you have to go long time, many iterates, but then the initial condition of your fluid approximation is random and has the form h of w. So this is the result, like this. And so the big problem, of course, is to show that this limit exists. I must say that in one dimension, we kind of solve the problem and fairly generally, because in one dimension you can solve things, especially in continuous time you have differential equations and you can describe functions there for which similar limit exists. But I think this is the first paper we deal in many dimensions. So if you formulate this result in RT, then of course you have a vector which has all components 0 and only one w, and you have to have some conditions on A, so A into the n, a little bit like Perron-Frobenius or something like this, and you get dominant eigenvalue and bigger than absolute value than any other, etc. Okay, so now I want to show this, in fact, prove this result for some specific situation, in fact, from which the whole research has originated many years ago, and that modeling the following situation. Then you have two populations. One population is a healthy population of cells, which contains perhaps many hundreds of thousands of cells, and they die and reproduce, so they're kind of in a critical regime. They maintain their numbers, and they fluctuate around their carrying capacity, call it A1K. A1 is a positive number, K is a large parameter, and then mutant appears. And mutant, if it's a mutation is successful, then it has supercritical reproduction, at least at first. And we're looking at a situation when mutant's carrying capacity is also proportional to K. And this is a picture when we start our model. So we have a population 1, which fluctuates around this line, A1K, not very random fluctuations are true, but they should be random as a critical process. And we have a mutant that appears, let's say mutant appears one cell, and they start dividing very fast. And slowly, of course, both reproductions decline, and we want to see we want to model the situation and obtain how mutant gets established, how it occurs. So here's a more formal description of this model. So we describe each population as a binary splitting. So you get 0 or 2 offspring, and probability of successful division depends on population sizes. So we had a model with Peter Yagas and Batutin and a number of people. Many years ago, we called it the bare bones evolution model, especially to model things like that. People maybe wanted to use it for some substitution in biology, I don't know. So anyhow, so this is a model, mathematical model, the binary splittings, and here probability of successful divisions written here. Initially Z1 is at A1, Z1 is A1K, and Z2 is 1. Initially is small, but these are the parameters of the model. And so how do we connect this model to random perturbation? How do we get dynamical system? Is by looking at the density process. So the density, when you take the numbers, population numbers, and divide them by K. So you look at that, And so you can see here, if you compensate these processes, take away the mean, then and combine means together, then you will obtain this system. Okay, so you get everything depends on the densities. When you divide by k, you can see here divide by k, you will get the density here x1 and x2, x1 and x2. So z's disappear and k stay. And so here we get etas because you have sum of independent random variables up to say roughly k. So the variance is over the k. And when you divide by k, variance get divided by k squared, and so you get 1 over root k. Size of the noise will be around 1 over root k, and etas will be over the 1. They will be just sums of. So this is, I think it's very easy to see if you look at this, compensate this, and you will obtain the system. And so here you have this, in these settings, epsilon is just 1 over k, and our dynamics is like that. So this is our f, is like that. So then let's study these dynamics, and we'll see what, this would be a very illustrative example of a general theorem, except that we can solve this example, and more general examples as well. So we can see that this f has 4 points, fixed points. One is 0 when nothing happens. And then you have 1 point is with these coordinates. So gamma here is a coefficient of the strength of interaction between populations, is a parameter between 0 and 1. And so you have this is a stable fixed point. So we assume that all the coordinates are positive, and we call it coexistence condition on the parameters. So they're positive. So that will be stable point. Just by looking at the derivative at that point, we get the eigenvalues less than 1. Now, this point is unstable. This and this are unstable. And they're saddle points. So they're saddle points because if we have no mutant, the point A1 for the density is a stable point for the population. For the resident population, divide by k, so A1 is a stable point, fluctuates around that point and comes back to it. But for mutant, it's not stable. And the same here, when you have no resident, only mutant is 0, A2 that's unstable point as well. So we start, let's say Z10 is Z1k, and Z20 is 1. So we translate it to the density. So we start at the point A1 and 1 over k. So this is our initial position. Okay, so this is our x0. And so I don't put bold. It's a bit confusing notations because we have too many x's, but I think you can follow very easily. So x without coordinates is just a vector, 2-dimensional x. So you can see this converges to this. So it starts near the unstable fixed point. So just as we mentioned before in the general result, now if we look at the Jacobian matrix at that point x1, it is given by that. And so rho is this number, and under the coexistence conditions, then rho satisfies this inequality. So rho is bigger than 1 and less than 2. And that's a largest eigenvalue of A. So it's unstable point, and rho is an important parameter, and that's the mutant. Rho over 2 is division of the mutant. So if you freeze, suppose you don't have reproduction of the dependent population, initially probability of mutant dividing successfully is rho over 2, which is supercritical. Now, I want to tell you what W is. So W, if you take supercritical binary splitting with probability of division rho over 2, it starts at 1, starting at 1, then we have this limit exists of that process. And that's exactly the W that appears in in the statement of the result, in the statement of the theorem. So let's go back to the general result. So this is this W. And now, of course, in general result, there's no branching, but there is another linearized system where W arises. But I decided to stick to the example and show everything on this example. Okay, so is it okay? Okay, so I cut and paste this, and okay, so here the result theorem by Baker, you can see this theorem that h of x exists. And here's a picture of h of x. And I tell you what you cannot see, that because the picture hid this, is that, okay, no, it doesn't move. It says that h has two coordinates, h1 and h2. It's a function. It's the limit of this function from R2 to R2, so it has a function h1 and h2. And it does not depend on x1 at all. It's a constant in x1, but they both depend on x2. So apparently it makes biological sense because it's a critical reproduction. So it doesn't depend on x1. It only is a non-trivial, and we don't know what the function is. I mean, we can compute it for given values of parameters, and we can write functional equations for this f, for this h. But we don't have a closed form formula for this h. Even in one-dimensional case, we don't have. Except for linear fractional, we can compute. It's also kind of linear fractional function in one dimension, but in two dimensions we didn't calculate it like that. So this is the function h. So it exists. So I'll show you the proof of that, because really I wanted to show you some really neat trick when proving this statement, because I think that I discussed it with Kais actually, this result, and he thinks that, well, how can you assume this? Because that's an important, a lot of meat is inside this assumption. Of course, if you can assume everything, then there's not much to prove. But I still think maybe it's not published. This result is not published, so I didn't give you the proof of that. But I still think it's okay to assume something and then prove certain result. But that's a heavy assumption. But in this case, we prove this assumption for, you will see for which f, for this particular f, but also, of course, we use property of this f, different properties, and we can show that h exists. Okay, so I want to give some steps of the proof for this result. So this has nothing to do with noise, it has nothing to do with probability. This is a purely analytical result on functional iteration. There's nothing random here. You take function f, you take fixed point x1, you have deviation, you start at x1 plus x over rho n, you iterate n times. Okay, so remember, f takes you away from x1, but divided by rho into the n takes you back to x1, and kind of it balances out that you have a limit. Okay, so let me show how we prove that. Okay, so first you move fixed point to 0, exactly, it's very general, so that's a very general elementary trick, that's why I can write it very easily. So you take f of 0 plus x minus x0, so take the function g. So g now, g of x0, g of 0 is 0. So now g has fixed point 0, and you can see the derivative at 0 is exactly the derivative of f at x0. So it's a, so it's the same. So it's a just shift, you just shift this function. So if you can write it like this, and when you iterate it, you get this. And you can see easily that fn is exactly gn of 0 plus x0. So if you want to show something about fn, it's just as easy to show about, it's identical to show about gn. Okay, not gn, but g sub n, yeah, n theta. Okay, so here's the step of the proof. So we need to show that this converges to h of x, well, give or take x0, and we do it in a very kind of big way. We show that this difference is summable. Okay, we show that this is summable. So this stands for the norm as I mentioned, so this is this, I didn't write norm, but write up, so that's a norm. We show that this is, how do we show it summable? We show this bound. And of course, this is summable, and this is summable, that implies that this guy converges. Now, how to get this bound? We use this estimate, okay? So actually, we need estimate for m and n, and m less or equal than n. So you get kind of recursion, so I'll show you in a minute. So you have a parabola here, you get a parabola p of x is rho x1 plus x. So we iterate this parabola. Very often in literature, in the noun work, we before came to the parabola x1 minus x, which was easy, a lot of known about this iteration. Rho x1 minus x is a classical case. I think that May came up with a different period doubling and chaos as things like depending on rho. But here we have an iteration of x1 plus x. And I'll tell you, so because we have this inequality, we can bound it. We can bound the function g by this function. So we need to show this. Okay. So we have a double recursion. So we iterate this parabola, but we start at the value that depends on n as well. We start at x over rho n, x divided by rho n, and we iterate this parabola. And now it's not trivial to show that these things are bounded. It's not trivial. So we need to show that supremum in nx will be some function psi of x, and it's finite. We need to show it's finite. How do you show it's finite? So this parabola explodes, and it clearly explodes. x1 plus x, you iterate, explodes. But every time you start with a smaller value, x over rho n. And it's remarkable that, so I'll show Sinet as a result, but let me just finish this idea. So if we show that this is finite, then we can clearly see that x and n is bigger than that, because you get rho times this plus something else, and you get this inequality, and that gives you this bound. And that gives you the bound for gm of x over rho n. That will be a similar bound. Now, how do you show that this is finite? And it's not only result by Schrödinger iterational equations, but there is a result by Sinetta in 1969, which is a not modification, but improvement on the classical result. And that's exactly what we needed. Actually, wrote to Eugene, and I said, we use his paper. He was very happy. He said he wrote this paper when he was a PhD student at ANU. So anyway, so let me just tell you about this result that on which the whole proof hinges, rests on this proof, okay? So again, now, forget previous notation, just I didn't want to rewrite in a new notation. That's a result from Sinetta, so I'll use his notations, okay? So we look at this equation for function phi. So S is a number between 0 and 1, F is a given function, and you want to solve this for phi. You want to show the solution exists and find its properties, okay? Now, so here's a statement. F satisfies the following conditions. So it's continuous, it's increasing, f of 0 is 0, f of x is between 0 and x, f of x over x converges to s at 0. So at 0 it behaves like s times x, like linear, with s less than 1. F of x is concave, and that will be increasing, and you need this integrability, right? So you need this, that should kind of be small, so it will be integrable at 0. Then Sinetta shows that this limit exists, okay? Solves Schrödinger equation. It's non-trivial. F of phi x over x monotone. Derivative at 0 is 1, and it has inverse. Okay, so this is actually it was in the Journal of Australian Math Society, this paper, and we apply this result with the function f of x of the inverse of our parabola p. Okay, so we take inverse of the parabola p. So p was rho x 1 plus x. So we take inverse. So s is 1 over rho. So we have that this limit exists. it solves Schroeder equation, and then we can easily compute x and n. So it's p n's iterate of x rho n, and we have conjugacy. So this one kills the next one, and so then we get this, right? All the n go away, but you get rho into the n phi x. So as n goes to infinity, rho is bigger than 1, so that goes to 0, it gets a derivative, and you get this result. So Sineta's result helped us to establish this bound, that when you do this iteration, there is a function which is finite function that satisfies this bound. And of course you need some more calculations to show that H exists by analyzing further iterates of G, a lot of algebra, but this is essentially, it's fairly straightforward, but this is essentially how it is done. That the norm of G is dominated by quadratic, okay? And probably some M is missing here. So if you look at the norm of G, is dominating by some quadratic, and quadratic is dominated by this. So of course, if we place this assumption on our function f in the beginning, then we don't need to prove it, then we get it for free, and then we get the statement. That's a bit like cheating anyway. So here's the main result. So the main result is, it says, take now t, we have t epsilon, now epsilon is 1 over k, so we have now tk. So now that this time is this 1 over log rho log k. And with respect to this particular question, we're saying that this is the time when the mutant gets established. So what does it mean, mutant get established? We mean by that the numbers, the proportion of the mutant is not negligible. So the numbers of the mutant is kind of proportional to k. If in the limit there is 0, it means it's not established. So if you take any constant c less than 1 over log rho, then this will converge us to this. So mutant numbers will go to 0. So it's not established until that time. But at that time, it is established. So in fact, at that time, xtk will converge to h of 0w as k goes to infinity. So in fact, this is the hardest thing to prove. Once you prove this, and iteration is not very difficult to do. But this is a main sticking point of the proof, to show that converges to some random point at that xtk. Okay, so now I'll show you a picture of the process. Okay, so it's a density versus approximation with random initial conditions. So this is time, iterations. Here we get native population started density at A1. So it was like this, and it goes down. So in fact, when you simulate this process, I mean, it takes quite a long time, that for a long time, this mutant stays very low to 0. So you don't see much about this one. It kind of stays long time at A1, and then this starts growing very fast, kind of exponential growth, and then takes this guy down, takes it out. And that's about tk. That's a point tk, time point tk. So this you get some kind of random initial condition, and you can see the green trajectory is in fact the trajectory of the dynamical system, and you have convergence to the fixed point, the correct fixed point, the stable fixed point. So in the long run, see, you get mutant gets established. In fact, it gets established very well. It kind of dominates. So A2 is bigger than 1, dominates the host population, so they kind of coexist like this. But instead of going to, as k goes to infinity, to unstable fixed point A10, now they converge to the correct fixed point. But now dynamics starts with a random value. So again, this is a mathematical result, and we're thinking hard, what is the biological significance of this? So if you look back, especially we talked to Peter Yagas, he invented the term, the veil of uncertainty. When you look back in the population, if you look at this and look back, and you know, maybe you cannot find initial conditions because it's so long back that the noise makes it random. So this simple approximation makes it random. So this is a phase portrait of this dynamic. So I want to show you for this particular map, you can see that this point is unstable, A10, and you can see all the arrows is where your system wants to go. That's it, without any noise. So they don't want to go to X1, you know, but our model says it you know, classical fluid approximation says it goes to X1, but you see the model wants to go to this point. That's, don't know why it does that. Okay, so this is the phase portrait. Okay, so I mean, of course, most important thing in I think in mathematics is the proof. So I would like to show some ideas of the proof of this result. Okay, so how do we prove this result? So of course pictures are nice, but they don't prove very much. May give you ideas how to prove it. Okay, so I'll just give some. Okay, so we have to define what W is. I already mentioned W. So here we define Galton-Watson binary splitting. So what you do, you freeze your reproductions at point x1, A10. So you look at the reproduction. So you have the resident population reproduce critical reproduction. So binary splitting, your probability of being 2 is half. So we can realize it like that. So here I forgot to write that U and J and V and J are uniform random variables. That's how we usually realize some random things using random variables. So here we look at this, and the mutant has a initially at time 0 probability of division rho over 2, which is bigger than 1. And so it is realized like that. So initially, the process, if you freeze the reproduction parameters given by the classical 2-dimensional binary splitting with coordinates y1 and y2. And the only thing is that y1 at 0 is n1 a1k, and y2 is 0 is 1. Okay, and so you know the density of that process by y bar. So it's yn over k. So we define this. And then the way the proof goes also shows you how the process behaves. We need to take time before our time tk, and we call this time nc. It's a log on the basis rho k into the power c, or 1 over log rho log k into the power c, and c is less than 1 and bigger than half. And so when we take c is equal to 1, it's exactly our tk. That's what we want. This is notation. So xn is our process. Xn is our density process that we want to show statement about this process. And here's our approximating process. So first we approximate it for n less than nc. We approximate it by the linear process. By the linear process, which is this. Okay, so this process is fixed parameters, don't depend on size, don't depend on k. That's how they go. The only thing that depend on k is initial position. Okay, so although I say this process does not depend on k, well, like this, but it starts at k. So initial values depend on k. So in some sense, let me finish this idea now. And after that, you can see that n is less than n1, so we don't really care about that. So we want to show that xn1 converges to h of this vector w. So, okay, so that's equal. So this we take discrete, we take deterministic dynamics after nc, so it will be, the time will be n minus nc, and iterate this random point where we end up with this linear dynamics. So we take linear, that would be a random point where we end up at time nc, and then we iterate it. So this is our approximation. So because what I wanted to say before, because we have initial conditions always also dependent on k or epsilon, is in fact we're dealing with the flows. Okay, so we have one extra parameter, which is initial condition. So we look dependence on initial condition as well as dependence on on time, etc. And you'll see how it plays out, that the long time gets converted to small initial condition. Okay, so we want to show. We look at this time n1, that's our time, and we want to show two things now. So we want to show this converges to h of w. So we want to show that this converges to 0, the difference converges to 0, and this approximating process converges to what we want. Okay, so this is quite simple. So clearly it's easier to show for approximating process that it converges to this random point at time n1, and then and show the difference converges to 0. Okay, so let me show first the second one because it's easier. I don't know why I made this red. Okay, so now have a look. So we get what's the connection between the k? So we divide by density and then 1 the time. So this is a connection. Rho into n1 is just the same as k. And so here let's have a look. So we take the approximating process at time n1. By definition, it is this. That's a definition. N1 is bigger than nc. So we have to take n1 minus nc. That's a typo. Like this. At that point. Now you can divide. You write what y and c. It's a density. So you take this your branching process, divide by k. This vector, and then you do add something, take away something in a little algebra. So you write it. That's your fixed point, and you get rho minus nc, and you look at this thing. Okay. So this is we haven't done anything. It's identity. It's identity. But what we want to use, we want to use the fact that I forgot to mention that in the first result we proved converges to h of w, and that's converged uniform on compacts. Where is this statement? This thing, you see. Limit existing, and when x belongs to some compact set, it's uniform. So because it's uniform on compacts, you can replace x by some other xn that converges to x. It will still give this limit. So now, having proven that, we're going to use it in our analysis, and that's how we use it. So here we have, we write it the way it is, right? So you get x1 plus something. So here you get something that goes to infinity, and 1 minus nc converges to infinity as k goes to infinity, of course, right? So that goes to infinity. And here we have something here, right, divided by that. So we want to show that this converges to this point, 0w. Because if we show it converges to this vector 0w, our result will tell us that that will converge to h of that 0w. Is that all right? Is that clear? If we show that this converges to this, and so we need to show this. Okay, so this guy minus kx1 that converges to this guy converges to 0w. And then if we show this, that this will converge to h of 0w. That's using uniform convergence in the first theorem. Okay, and this is very easy to show because you do it coordinate by coordinate. So you know the first coordinate of this I'm showing it to myself, but you can't see my screen on my computer. So here you see the first coordinate of this guy is a critical process. So you know everything about critical process. And Kostya will tell you everything you want to know about critical process, right, Kostya? You know everything. So the mean is A1K because you start there. The mean does not change. The variance is less than n times this guy. And so we get this bound. I look at the variance. And therefore, if you look at this, C is bigger than half and less than 1, you get the first guy converges to 0. Okay, just from these calculations of the second moments. But what happens to the second coordinate? Well, second coordinate is a supercritical Galton-Watson process. So we know that yn, so y to n over rho into the n converges to w as n goes to infinity. So this is nc goes to infinity, so we get converges to w. So that establishes this result. So this one actually is indeed was easy, corollary to the main statement. Now it's a bit harder to show that the difference, that this is a good approximation, that again, it has a simple steps and more complicated steps in this. But by the way, I forgot to mention that this idea, this idea of approximation, that goes back to Andrew Barber. There was our paper like 2015, the paper with skies and higher, and that's we toiled for many years trying to prove something, and we couldn't do it. And Andrew came up with this, exactly this very idea, we're using it because it's a good idea, so we have to use it. So it was good. So now the next thing we want to show that this guy goes to 0. So we showed that this guy converges to what we want. So now we have to show that this minus this converges to 0. Again, we split it into 2. One is we look at X and C, okay? And the other one, so we kind of take a random point and iterate it, and then what's left over, we have to do it like this. So we just add and take away this term, and we show that both terms converge to 0. So I'm going to start with a simpler term, and that's this term, because dynamical system is when you can start from anywhere, and then you be that many iterations after that. So what is the difference with xn and this? The only difference is that this is a deterministic iteration starting at this random value. But the difference between this and this is that you add noise at each step. So using the difference equation for definition of xn, you do backward iteration, and you obtain this recursion for this guy. Okay. And so now, of course, you can see that if you use Lipschitz, if f is Lipschitz, then you get kind of Gronwall, and you can control everything. And that's exactly what we need. In the general theorem, we assume that f is Lipschitz, but it's also assumed in a classical situation, so there's no drama. So we assume it's Lipschitz. Here we don't have to assume it because we have a specific map that we can compute, and we can see it is Lipschitz. And here, globally, we can have the Lipschitz global constant does not exceed 2. And so in this case, again, it's a direct calculation for this particular function, but of course we can make an assumption here like that. And then we get kind of a recursion like this for the norms. And the rest is very, it's like a Gronwall. The rest is basically like a Gronwall. So we can just do it. And when we do all the calculations and housekeeping, we get that if we take C close to 1, then we get this term that will go to 0. It does the job. So it's pretty rough, but it's good enough bound. Okay. So that was also a simple term. We have some random point, and then you replace this by deterministic iteration from that random point. But now, of course, you have to show this. And that's actually the hardest part in the whole thing, because I mean it's not hard in the sense that it's totally unknown. It is very much known, and we did this with Andrew in our paper with Pavel when we did one-dimensional birth and death process, where we showed that random initial conditions arise. In this approximation, you couple linear up to time and C, you couple linear and non-linear, and you manage to couple it so you get successful coupling with probability 1 in the long run. So here you have to do the same. So you have a density of our process. So you want to show that this is converges to 0 as k goes to infinity. And when you translate, when you go back to theorem 1 that things converge to h, you see that that's enough to show this statement for the processes themselves without dividing by k. So you need to show this thing. And this is done. So when you translate this rho and then c, so you get k minus c. So you need to show this statement. Okay, and this you somehow you can't do by moment calculations. You have to do we do it by coupling. And that's a little bit tedious. I'll just show you a couple of slides on that. But again, it's well-known technology. And the only thing why it's tedious here is because it is two-dimensional. So here what we do, we construct a Galton-Watson binary splittings, which are lower and upper one. That our process sits between the two. And then we look at this thing. So here we look at, take some numbers like this, and using the same random variables in definition of our process Y, we get the lower process, lower branching. We get this RK like this. We get here some powers of K. So we mimic, we freeze Z. Remember, in our process X or Z, this probability was Z. Okay, there was Z probability, but here we freeze them at some particular level at K, and then so you get this lower and upper, and L2, or maybe this is something like this, and you do stopping times. First time you come to that level or go to that level, and so what it says, components of the 10 live small neighborhoods of unstable fixed point. And then we take a time, the coupling time for above processes, and we have this inequality by construction. And tau bigger than n, we have this inequality, so I have to control this, and the rest is, for example, to show that for the second coordinate, we say we want to show this, and this successful coupling happens by time and c. We do these calculations, and as I said, actually it's more work, but it's all in the paper. So if somebody wants to see, probably I lost my train of thought here, but this is how you do it. You construct two branching processes, which is not population dependent, but with fixed K, and you show that this coupling occurs. What I wanted to say, just a few words, if I have a few more minutes, is just the literature in this long developing project. And of course, we started to do this problem, and when Haya Kaspi, she's a probabilist from Technion, she works on very, like local times and things like this, Gaussian processes, very theoretical person. She asked me, what am I doing? And I showed her, said, okay, let's solve it. And we've been solving it for a few years, and we couldn't do it. And until Andrew, I gave a talk at some conference where I gave a wrong proof of that result, wrong result. So Andrew heard the proof and said he knows how to do it more or less. Well, we did not do random initial conditions. So this is a paper with Andrew, escape from the boundary in Markov population processes, which is fairly different type of idea. There we have random shift, but this is the first paper which we actually very simple birth and death process where we have random initial condition and fluid limits in one-dimensional thing. And then it turns out that you can apply this technology in discrete time. And for example, polymerase chain reaction, where you start with very low numbers of DNA and you multiply them. And we have our theory tells us that the number of multiplications should be log K. So we know exactly, and K in this PCR polymerase chain reaction is actually Michaelis-Menten constant, some chemical constant. So it would be interesting to get a chemist to test our theory. Yeah. So, but we haven't done it yet. It would be very nice to do it if it's true or not. Okay, so this is this paper, and with Jeremy Baker and Kais, we wrote this fairly complete description what happens in stochastic differential equations in one-dimensional. Also, it's very, and that's in that paper actually. We had the idea how to get the H of W. The H transformation is I think is an important one. As I mentioned, that's doesn't seem to appear in the literature. And this is a paper on bare-bones model. So yeah, and of course, Kurtz is a famous paper by Kurtz. It has thousands of citations. That's a fluid limit. And this is a famous paper. That's a paper by Sinetta that helped us to prove this, solve our problem. And this is the final slide, so I thank you for listening to this talk. Thank you.
Thank you, Fima. Thank you for a very interesting talk. So we have time for questions. Please unmute yourself and ask your question if
I have a question. If you can hear me.
Andrew is supposed to have answers, not questions.
Well, it's just that your iterates, back iterates of this function f,
Yes.
lead you to some sort of functional equation, this Schroeder functional equation. And the branching process limit random variable has a functional equation defining its probability generating function or whatever.
Yeah.
But these are different equations, I guess, because your H is looking at the nonlinear process, isn't it?
Correct. Yeah, they're different. They're not generating functions. But
that's right.
But the series,
but
sorry.
Is there some relation between them?
Yes, the relation is the series of Schroeder equations. It is applied, classically applied for generating functions, because we know that's the distribution of the nth generation, but there is no need, you can apply it to anything. So that's Schroeder's equation. The only thing I want to mention, and I didn't say, that in many dimensions, the series is very incomplete. It's quite complete in one dimension. If you have higher dimensional Schroeder equations, not so much is known about that.
Right.
But in our case, because we work with norms, and we could dominate the function f or g by quadratic, also exploiting quadratic, we're lucky that it actually, they gave us what we wanted to do. Yeah.
Yes, I mean, in some sense, even in the multidimensional case, your random variable's one-dimensional. So
no, random variables multidimensional. Why are they they're multidimensional? Why do you say they're one-dimensional?
Well, your W, one of its components is fixed at 0, and the other
that's right. In the limit, yeah.
In some sense, there's something which is saying the iterates are such, you set up the equations so that there is only one coordinate in a sense which matters. And
this is because this is because similar to a linear case like multi-type branching, when you have a largest eigenvalue, it grows in the direction of that eigenvector. But
That's right.
row into the n kills everything else. The same is here. It's like in this approximation, it will kill. Row into the n will kill everything. It's kind of lives the clever words lives on unstable manifold.
Yes.
So it lives on unstable manifold. So whatever it is, and in fact, I have a proof of the general statement where you do exactly that. You take a vector x and where is the general statement? You shouldn't quote it because first of all, it's not published, and secondly, there's not enough assumptions. That's not that. This is new result. So you take a vector x, and then you put it into say you assume that a eigenvectors form a basis, decompose it according to this. Rho is the largest eigenvalue, and eigenvalues get killed. So you can transform this vector equation to kind of scalar by multiplying by x, and then rho into then gets killed. However, h, you can pointing out in the wrong computer. H is multidimensional itself. So it will depend only on one coordinate in some sense, but all of the coordinates of H depend on that.
Right, exactly.
So in a sense, there are functions of one variable. And so as marketing goes, so we're saying like what we said, that H summarizes kind of nonlinearity in the whole system.
Yes.
The whole system, nonlinearity comes to H in a way, and that's what, guys, what did we say? It splits up, H does nonlinearity. And so I think what we need to do, I think the correct way, the correct thing is this. The limit is that. The fact that you get rho into that, it doesn't really matter because that scales in the same way. But this kind of, it appeals to me because they both act in spaces. So A is a linear map. You get pulled back by linear and you get forward. Also, by the way, in the statement, the main result, n could be anything. you can go backward iterates as well. So when you take log k, you can take plus minus n, it doesn't matter. You can go back with that. So what is interesting, even from biological point of view, what is age? What does it mean? No idea. We don't know this. But I think that was a step after we had the paper on birth and death process. To example, that was, I think, the realization that this works. In one dimension, you can get very nice, especially in continuous time, equations to find age. Some nice tricks. But in general, when it exists, I did some research. There is a theory of Hartman-Grobman that talks about linearization of functions. Okay, and usually it's a local thing. If you have a fixed point, you can linearize it near a fixed point. Hartman-Grobman theorem. But there are results when this Hartman-Grobman is a global. This result is not quite Hartman-Grobman, but it will imply there is global linearization. If you look at this, you can write f as a combination of f and n to the n. So yeah, many years ago people wrote, but you need some. So what you need, a linear function plus a function with a small Lipschitz constant, then you get some global Hartman-Grobman. Anyways, you can see it's a work in progress, but this actually was published. I didn't mention it was published. This is on establishment of a mutant paper with Jeremy and here. This one, it's recently came out. This one, this thing.
Okay. Anyone else? Other comments, questions?
I have a simple question.
Fima, sorry, do I have the floor?
Hi, Ross.
Please, Ross, go ahead.
Fima, yeah. But I think you answered the question already, which is that you can't say much about the distribution of this limiting random variable.
Yeah, in our case, we can say exactly because we know it's I think it is a, we know exactly this, is it exponential? I don't remember. You have a binary splitting Galton-Watson process, so you know exactly the distribution.
Okay.
We know the distribution of this in this example. And in general, it's a distribution that comes from norming linearized system, and you can usually compute it.
Mm-hmm.
But in this case, yeah, for sure we know. Also, I did not actually say everything about this paper, only some things, but other things which are interesting maybe for establishment, because h of 0 is 0, it tells you exactly the probability of establishment of a mutant. I can find now the statement. It exactly gives you the probability in the paper. Let me have a look. I had some, sorry.
Went into your courses there, Fima.
I give it to students to prove, maybe they'll do it. See? So probability that mutant gets established is 1 minus extinction probability of the Galton-Watson splitting, and we know this. You get 2. This is a probability of mutant gets in this model. Who knows this model is correct or not? Probably this is a weak part that we don't know if the model is correct. And distribution of W, we also had it. I knew it. I don't know if I wrote it here, but it's in the paper. Let me look at the paper. It's certainly we know this. So this is the paper. This is the front page of the paper, and where's probably hard to find W. But if you like, I can send you the paper.
Sure.
Where's W? We had W somewhere. Andrew, do you remember distribution of W?
No, I don't remember.
It's exponential, isn't it exponential?
There is a functional equation that.
No, but this is binary splitting, you can solve it.
Ah, in the binary splitting, it's exponential, yeah.
Exponential, so it's exponential.
Yeah.
It's a binary splitting.
Yeah.
So we see in the paper, that's the point when to do proper mathematics, sometimes notation is really pretty bad. Because what the referee said, how come log rho k is an integer? So you don't have an integer, you have to, wanted to put integer valued everywhere. So you get fractional parts everywhere. So you can't read the paper. So the whole thing is you have to cross it out. You know, sometimes being too pedantic, I think it is not good. So, but Andrew, your approximation works very well. And I can't find W, but maybe here somewhere. It's exponential, that's right. So this is the things I can show you, all these calculations. They're straightforward, but they're a bit tedious. So I don't know whether, I don't know. I think now the main theorem. But what people said, I tell you what the referee said. He said such an obvious statement, but h of W is not obvious, but many things. So why do you need such a big paper for such an obvious statement? What other models can you do with this? Don't know, W. Must be exponentials. We write it somewhere, maybe. Yeah, can we actually see it? Manifestation of this result. So the noise accumulates over a long time, and we were thinking about Big Bang, but we don't know where to put noise in Big Bang equations. So we will get there. Well, PCR is good. I talked to some chemists. They had an offer. They'll test the theory. They'll test my theory. Our theory will be tested in PCR machine if we pay them. So I had an offer, but we didn't get the grant, so we can't pay them. So I have to get on a student. They all have PCR machines today everywhere. So it's not so hard to test, I think. Of course, it's dangerous to test. If you test it, it's not true. What does it mean?
It reminds me of someone, you know, too many tests. Anyway.
I can't find that.
Okay.